All right, let's get started. All right, so you have your PS3 is out, due tomorrow, Friday if you take a late day. Are there any questions about that or anything else? Yeah? Mm-hmm.
One of the test cases specified symmetry with different spacing that was to be considered equal. But then another test said two different strings with spacing not equal.
It has nothing to do with characters and spacing. It has to do with tokens. So tokens are text separated by white space. So how many tokens are in this string? 3. How many tokens are in this string? Can't be the same. Different number of tokens. At a minimum, they have to be the same number of tokens. In addition, they need to match up. So, if we had A, B, C, D, 3 tokens in each, but the C token does not match the CD token. Yeah?
The method in my page, so I used the 5 conditional like you said, and I made it work, except at the end, I didn't have a return outside of all my if statements, so I just returned an empty string. That's fine.
For which problem?
For get my page. Like it worked, but so for under, like.
Okay. All right, I think I know what you're saying. So get life stage. If you write it like this, if you say if age is less than 2, return baby. And then you say if age is between 2 and whatever, return child. And if, between 13 and 19, return teen, and so on. What happens is the Java compiler knows you're supposed to return a string. And it looks to make sure that in every case you do return a string. Now, you may look at it and say, yeah, it will return a string in every case because the last one is if age is greater than something. But the Java compiler, for whatever reason, isn't able to convince this. So it's going to complain that you're not returning a string. Now, your solution at the end was to say, return empty string. Because you know that will never be executed. That's fine, but there's a cleaner way to do it. What's a cleaner way to write this conditional? Yeah?
Put solution equals and then maybe or whatever, and then solution equals child, and then on the bottom puts return solution.
No, I don't think that's cleaner. That's just another way. Yeah? Right. You do if, else if, and anyway, the final one would just be an else. Then the Java compiler is happy because it sees that you do something in every case. It also makes these conditions simpler. Because if you have the else if, the first condition is going to be if age is less than 2. If you get to this point, you know that age is not less than 2, so you don't have to check that again. You just say if age is less than 13, I think. So it simplifies your conditions as well. So I'd recommend using an if, else construct. Yes?
Along with whatever it's checking, return null if you don't get a string.
Well, okay, so he's asking, could you return null? There's no need to return null. This method ought to return something in all cases.
That's just the way that I got my code to work, I guess.
Right, well, it would be incorrect for the method to ever return either an empty string or a null. So your code is only correct because it never hits that return statement. Be cleaner to do it this way. Yeah?
So when I declare the new scanner, it says that the scanner, I get like an underline, like an orange underline, so the scanner is never closed, so it doesn't cause any problems.
Okay, so this shows up a lot, and you'll see it in my code as well. There are certain objects, resources, like scanners, files, and so forth in Java that when you open them, Java wants you to eventually close them. If your scanner is reading from a string, it doesn't matter whether you close it or not. If your scanner is reading from a file, then you want to close the scanner so the file gets closed. The problem is if a program runs for a long time and keeps opening files to read and never closes them, there's a limit to how many open files a process can have. And eventually the opening will fail. I haven't mentioned this. I mean, you can, if you want to get rid of the warning, just the last thing close the scanner. I haven't talked about it because there's a better way to close the scanner. We'll see in a week or two. I wouldn't worry about it right now. Any other questions? Okay, well, we were talking last time about searching loops. Let's continue looking at searching and accumulation loops, and we're going to move to optimization loops. So right at the end last time, we wrote this loop right here that returns the number of positive integers that are factors of n. And this is an accumulation loop, sort of a special kind, a conditional accumulation loop. It only accumulates some of the things. But you can see it has the bones of an enumeration loop on integers. So we got int I equals 1 while I is less than or equal to n. And I made the mistake, I'll tell you, I make a lot. What's missing from this? Obviously didn't test this last time. Right, I forgot to increment I. Actually, I remember now I was trying different ways to increment I. Okay, it has an accumulation variable, which it returns. And during the loop, it occasionally increments that accumulation variable, but only when it finds an I that divides evenly n to n. So this counts the number of factors. So for 6, it would count the 1, the 2, the 3, and the 6 as factors. So that was the accumulation loop. We're gonna use this method in a second. That's why I'm going over it again. All right, so this is similar to the kinds of loops you're writing on the current assignment. Right, now let's consider this problem right here. Returns an integer token from numbers that has at least n factors, and returns 0 if there's no such token. And we're going to assume that the string only contains positive integers. So for example, if we give it 2, 3, 7, or we're looking 1, 2, 3, 4, 5, 6, and ask, is there an integer in there that has at least 4 factors? We would return true because the 6 contains 4 factors. So what kind of a loop is this? Is it an accumulation loop, searching loop? Yeah? Okay, it's a searching loop. Someone else tell me why it's a searching loop. How do you know it's a searching loop? Yes?
There's only one token to satisfy a condition.
Okay, we're just searching through, trying to find a token that satisfies the condition. Once we find it, we don't keep looking. So it's searching for something with a property. So to implement it, we need to go find inspiration. Let's go find a searching loop we've already written that deals with strings. Well, actually, this string is going to have to be turned into a scanner. We have to create a scanner to read from it. So let's look for that kind of loop up here, see if we can find it. That one takes a scanner directly. That one we didn't do. Okay, well, we don't have exactly what we need. But this is going to be a loop that, despite the fact that it takes a string as a parameter, it's going to be a loop that consumes a scanner. So let's go find that at least. This takes a scanner and does its thing. So let's copy this, a scanner searching loop, and paste it in there. Okay. Now, how can we fix this up? We got a string of numbers, but what we got to do is go through it as with the scanner. Yeah.
Rename tokens to numbers.
Well, we could try renaming numbers to tokens, but what would the problem be if I made this numbers? Right. There is no has next method on strings. So renaming that to numbers isn't the answer. What's your answer? Right, we need a scanner. We'll call it tokens because we're already using it by that name. So I'm going to say scanner. So we use a scanner to break this thing up into the individual numbers. Okay? Now let's think. We read the scanner, while tokens has next. What ought to we, if the loop ends, what should we return? I think I was saying true and false, but in fact, we're supposed to return the actual token that has the number of factors. So how do we know what to return? What would it mean if the loop ended? What's it mean when a searching loop ends? Yeah.
It needs to either found what it's searching for or it hasn't been returned.
Well, when I say end, I mean, what does it mean if it reaches this return statement? If it reaches this return statement, it did not find what it's looking for. Because it found what it's looking for, it returned already. So how do we know what to return to indicate it did not find? Yeah? Why negative 1?
If it's looking for positive factors, negative 1 will never be the answer.
Okay. What do you think? Right. The spec right here says what to return. So there's nothing wrong with negative 1. It's just it isn't what it says what to do in this case. If it said return negative 1, then we could return negative 1. But the Java doc says return 0 if no such token. So we're going to do what the spec says and make that return 0. Okay? So what's wrong down here? Yeah? Right. The place, she said token needs to be an int. The place that we copied this from was dealing with the tokens as strings. We got to pull them out as integers. So instead of asking whether there has next, I'm going to say has next int. And then rather than asking for the next string token, I'm going to ask for the next int token. And number, just to be more descriptive. Okay, so far we haven't done much. We just have the skeleton of a loop that will just grind through all the numbers in the stream, in the scanner, and then return 0 when it's done. So what does it take then to finally make a searching loop? What do we need to do to change this into a real searching loop? Yeah. Okay, you need an if statement to test whether this number right here satisfies a condition, has at least n factors. Okay? So we need to say if number has at least n factors, and what do we do if it has at least n factors? We return it. So far, almost without thinking. Specification was to decide what to return on failure. So now comes the only creative part of this whole thing, which is how do we decide if a number has at least n tokens? Yeah. All right, we have this handy method up here that'll tell you how many factors a number has. Okay? And what's it called? It's called number of factors. So I'll copy that name. We'll come down here. So if number of factors of number, so we'll get the number of factors that number has, and what has to be true about the number of factors? It has to be greater than or equal to 4. Oh, very good. Right. We're not checking to see if it has at least 4 factors. It's whether or not it has n factors. So we'll compare it to n. Thank you. And there's the searching loop. So most of our time was spent just getting the boilerplate there. You know, the code that is common to all searching loops over scanners. Had to tweak it a bit to deal with integers. And then we just have to put in a test to check whether the number of factors is in the right range. Now, all too many of you, I think, would say, I need to calculate the number of factors. You know, when you get to this point, I've got to calculate the number of factors and would proceed to write a nested loop to do that, maybe. Okay? The point is, when you get experience, you can get a loop inside a loop. If you really do find yourself in a situation where you think you need to have a nested loop, maybe the method you need already exists. If you're lucky. What if the method you need doesn't exist? Write it. It's a lot easier to go and write and test a method to do what you want to do than try to nest its loop inside this other loop and get all confused. I don't recommend nested loops for a while. So this in a sense, this really sort of a nested loop deal, because as we loop over tokens and we call number of factors, we end up looping over possible factors. But it's just, this method can be used and tested independently of this one here, so that we don't need to worry about them interfering with each other. All right, so there's a searching loop that makes use of, it also illustrates calling another method from inside of a method. All right, any questions, any other questions I could answer about this? Your next assignment will involve plenty of searching loops and optimization loops, which we'll look at later. Good? Yeah.
You have a scanner, like on tokens, like underline it says scanner not closed. What do you do in that case?
Close it. He asked the question I answered 5 minutes ago, which is what to do about that underlying tokens.
Closing it yet. There's another thing that Coach suggests to do, which is called suppress warnings.
Suppress warnings just says ignore this.
It's pretty much what we want to do.
Sure, but there's no problem just letting the warning. My answer is right now, just let it be. And we'll talk about closing scanners later. But there is a close method if you want to call it. Okay, so you could, oops. If you really want to, you can just say tokens.close right before you return it. And you can say tokens.close right before that return, and lo and behold, the underline goes away. But there's a better way to do it than putting these closes in. There's a way to have it happen automatically when you're through with it, which we'll talk about later. For now, I'm happy you just live with it. And what the other student says, it'll suggest suppress warnings, so you can do that. I'd rather see the underline personally than to see that suppress warnings right there. So that's okay. Any other questions? All right, let's write another loop. This method is called all R prime. So it gets a string, again, containing numbers. And the question is, are all those numbers prime numbers? In other words, the only factors are 1 and itself. So 2, 3, 7, 11 are all prime, and so the method will return true. But 2, 3, 7, 9 are not all true. What kind of loop is this? You could view it as a searching loop. Basically, you search for a non-prime number, and if you find it, you return false. And if the loop runs all the way to the end, you return true. So you could view it as a searching problem. But I'm going to view it as an accumulation problem because I've noticed that students in my office are having a hard time doing accumulation loops when the method returns a Boolean. They're fine with accumulation loops that return integers or that compose strings, but not when it returns an integer. So let's view this as an accumulation loop. Okay? So I'm going to, even though this isn't an accumulation loop, I'm going to quick copy this and turn it into the right bones. Oops. Let me just paste in a loop here and doctor it up. I'll call the scanner. I'll do that. While tokens has next int. We got to do something in there. And we need an accumulation variable. Okay, so accumulation loop needs an accumulation variable. What would be the type of our accumulation variable? Boolean, and we'll call it all prime. And should we start it out as true or false? There are only two choices.
True.
All right, how many think true? How many think false? All right, here's how you decide. Suppose there are no tokens. Suppose the string is empty. So, so we're going to set this to something. If there's at all, and we'll go and we'll immediately return all prime. So the question becomes, what do we return if there are no numbers? True or false? How many think that all the numbers in an empty string are prime? How many think that all the numbers in a empty string are not prime? Okay, those of you that raised your hand, tell me the number that's in an empty string that's not prime. 0 is not in the empty string. There are no numbers. It is a correct statement to say that all the numbers in an empty string are prime. It's for each number that is true. There are just no numbers. Yeah?
You could say that which number in an empty string is prime.
Well, if someone asks, is there a number in the empty string that is not prime? What's the answer? No. There's a difference between if you say for all versus there exists are two different things. So any property is true of an empty string. Any property of strings is so. Are all the numbers in an empty string prime? Yes. Are all the numbers in an empty string not prime? Yes. On the other hand, is there a number in an empty string that is prime? No. Okay? That's the conventional way of dealing with it. And I've had long arguments with students about this. But you may have, I don't know if you've ever studied logic to the point of looking at quantifiers, but they're universal and existential quantifiers. So if the universal one says for all things, some property is true. So any property of the form that says every element of a set has some property, that's just automatically true. And any question that says, does there exist an element in a set with some property, if the set's empty, that's false. So what we want to return in this case, if the thing is empty, if there are no numbers, is true, because it is true that all of the numbers in an empty string are prime. All right, that's that. Now what do we do in the loop? Do not write an if. Let's do this without writing an if. Yeah? I just cut you off, right? You wanted me to write an if. Well, what would it look like if this were arithmetic? You wouldn't write an if. What would you do? Suppose you were adding up all the numbers. Yeah?
Sum equals sum plus has.
Right. So it would be sum equals sum plus something. So let's do something like that. Tokens equals tokens. Then we got to combine them somehow. Okay? Now, we're looking at let's pull the number out here. Let's pull that number out. So at any given point, what am I doing? All prime is my accumulation variable. At any given point in the loop, all prime should be true if everything we've seen so far is prime. And it should be false if it's seen anything that's not prime. So what I'm going to do, how can we tell if a number is prime? Yeah.
We can use the same thing we used for one factor, starting the previous method, n factor, except instead of n, we just take greater than 2.
Okay, so something is prime if the number of factors is exactly 2. Okay. Well, it's funny because I don't have it. So that thing's going to be true or false. The expression in parentheses will be true if number is prime. It has exactly 2 factors. It'll be false if it's not prime. How do we combine that with all prime? So we get the right answer at the end. Yeah? Right, we AND them together. You don't add them together. You AND them together. So let's see what happens. All prime starts out true. What happens if the first number is prime? What will the new value of all prime be? It'll still be true, because we would have said all prime gets all prime, which is true, and number equals 2, which is also true. So we AND the trues together, we get true. What happens if the next token is true? Is prime? Still stays true. What happens if the next one is not prime? Then we AND together true and false, we get false, and that goes into all prime. And after that, it can't change. Once it becomes false, it'll never become true again, and we'll return false. So that's how you can write something that returns a Boolean as an accumulation loop. You have to AND things together, or you have to OR things together as you go. That said, why might it make more sense to write a searching loop in this case? Yeah?
You pass in like a really long string of numbers, but then it's like the first one is prime and it's false and not work.
Right. A searching loop in this case would be more efficient. What he said was, imagine a million numbers in the string, but the first one is not prime. If you write a searching loop, as soon as you find a number that's not prime, you can return false right there. You don't have to look at the rest of the string. So that's fast. But this loop would have, even after all prime becomes false, and you'd continue looking at the other million elements in the string, which is a waste of time because there's no way it can become true again. But I just want to show you it's possible. Now I want to tell you something else. The way ampersand works, if this is false, it doesn't even bother calling number of factors. That's called short-circuited evaluation. Why, if this is false, does it not even bother figuring out if that's true or false? Why does that work? Yeah. Right. No matter what the value of that highlight expression is, whether it's true or false, we're ANDing it with something that's false, so the answer is going to be false. So Java doesn't even bother it. It just skips. Yeah.
To make this loop more efficient, for the like the example we said, if you have like a million, and the first one false, by just adding in the while loop and all prime equals true.
Well, you have to stop. Oh. Yeah, you could make it. So he's saying we could do this. You don't have to say equals true. You just say all primes. All prime. So that would stop the loop as soon as it became false. So it's no longer really a counting loop or an accumulation loop. Let's just write it as I keep talking about making a searching loop. Let's make it a searching loop. So we'll call it all prime search. Okay, so I don't need an accumulation variable anymore. Okay, so we're going to have a loop. We get the number. So the idea is, think of this as we're searching for a non-prime number. As soon as we find it, we're going to return false. What if we don't ever find a non-prime number? What do we return? All right, so we will return true if the loop terminates by going through all the elements. And then what should go in here? What goes inside of a searching loop? Yeah? All right, an if. And so we're looking for a non-prime number, right? Okay, so we'll compute the number of factors. So if the number of factors that we see is equal to 2, not equal to 2, what do we do? Return false. Yeah? No, the spec says that all these numbers have to be positive. It's one I'm ruling out. One is not prime. And one has only one factor. So if we said greater than 2, it would treat 1 as prime. That's why I want not equal to. That's definitely a fun point. So this is the same. This is a different implementation of the same method that is a searching loop. It's more efficient because it can terminate early. And that's true of a lot of times when you write what would naturally be an accumulation loop, but you're using Booleans. You can do this sort of trick. Because there are only 2 possible Boolean values. All right, so we've seen an accumulation loop and a searching loop right here. Any last question about those? Yeah?
Maybe combine the two so that it searches for everything out of the default and then tells you which ones. So that you kind of combine the searching information.
Yeah, you could use an accumulation loop that, let's say, it got rid of all the non-prime numbers and just returned the prime numbers. So you'd be accumulating a string. And that would definitely be an accumulation loop, a conditional accumulation loop. It would have to go through all the elements. Any other questions? Okay, I want to introduce now a new kind of loop called an optimization loop. In an optimization loop, is characterized, you've got a collection of things, a range of integers, a string, a scanner, eventually an array, a list, whatever. And you're trying to find the element in there that is best in some sense. So there's always, when you describe something that is appropriate for an optimization loop, you want a superlative adjective. So like this one, it returns the number with the largest cosine. Or returns the largest character in S, which by that I mean the one with the highest Unicode value. Or finds the longest token in a scanner. Okay? So all those are, you've got largest, and longest. Or it could be smallest, or prettiest, or ugliest, or smelliest, whatever. When you see a superlative in the specification, think optimization. Now, will we be able to write an optimization loop that does not look every element in the collection? No, it's got to look at every element because it never knows what the best one is. The best one could be last. So it needs to keep looking until it finds the last element. So it'll be like an accumulation loop in that sense. It's got to look at all the elements. Yeah?
What if nothing we input is a sort?
Well, he's asking, what if you know the list is sorted? Suppose you had a list of things and they were in ascending order. You're supposed to find the smallest. Well, there's no need for a loop in that case. You just take the first thing in the list. Yeah?
So what are you supposed to deal with? Like there are two values that are equally large, so equally small.
Okay, so he said, what do you do if there are two values that are equal?
Can I pick one?
Pick one. I mean, if it's numbers, if they're equal, they're both, say, 7. It doesn't matter which you return, which 7 you return. But yeah, in general, if two things are tied, you just pick one to return. I thought you were going to ask a different question. There's another problem that always comes up with optimization loops. The problem is in specifying what it should do. Can you think of sort of a problem? Yeah.
Sometimes have problems where what to find with the largest character is.
Well, yeah, he said, is there a problem defining what the largest or best is? That's true. That's not what I had in mind. Yeah. Well, he's saying if you have a list with 10 million things in it, you got to go through all of them. That's sort of inevitable, but that's closer. That's sort of at the wrong end of the spectrum for what I was wanting to get at. Yeah?
Does it have to do with the way in which it's sorted?
No, it doesn't have to do with how it's sorted. Yeah? Right. What if there's nothing in the collection? What if the string is empty? What if the scanner has no tokens? So the question always comes down to, what do you return if the collection of things you're looking at didn't have anything in it? And again, that's something that has to be specified. And there are two common ways of doing it. One is we say, we require that the collection be non-empty. Right, you can see I've done that here, where n is required to be at least 1, where s is required to be non-empty, where the scanner is required to be non-empty. Then you don't have to worry about it. The other case is you allow it to be empty, and then you'd have to say in the Java doc what it's supposed to do. So let's look at this first one. Find the int with the largest cosine. So you're looking for numbers from 1 to n and see which has the largest cosine. What would be a reasonable number to return to indicate that there aren't any numbers in the interval? 0 would be fine, or -1. Because the only valid responses are going to be positive integers. Because you're starting at 1 and looking on. So a lot of times you just pick an impossible answer, like 0 or -1 or a really negative number to indicate failure. You're supposed to return the largest character in S. What character could it return if it's not empty? If it's empty, rather. Well, he said $. Well, what if $sign occurs in the string and happens to be the largest element? Well, there are no empty characters. They're just characters. And any character could be in a string. So there really is no good answer. All the characters are possible return values. Any character in Unicode could be the largest one in a string. So there really isn't any good answer in that case. What we'll see eventually is there's a way to not return and to instead throw an exception. When we see it, you undoubtedly have seen exceptions being thrown. I've referred to that up to now as your method crashing because it does something it shouldn't do. So we could cause find largest char to throw an exception. Now you may think, man, why would you ever want to throw an exception since it causes the program to crash? The answer is, not only can you throw exceptions, you can catch them. You can deal with exceptions. You can find out exceptions occur and do something about it. But we'll leave that aside for now. What about if you got to return the longest token from the scanner? what would be, so you're returning a string. What string could we return to say, oh, the scanner's empty? What string could not possibly be the longest string in a scanner? An empty string. By definition, that's not open. Okay? So let's take a break and we'll see how to write a optimization loop. Here, what do I click? Peter, you in here?
thought you were in one and now you're confused. No, that's the first one you wrote. No, the one that's given to you isn't for Latin. The one that's written is
Wow, you have 19 subscribers?
you got to write to speak Latin. You got to write to speak Latin.
So what's happening? Is it showing up?
The one that's given to you tells you where the first vowel is.
I have this as unlisted.
Oh, yeah?
No, it's going to a file locally, right?
Yeah.
Okay.
I got this wallet called it's called hide and seek.
First vowel. Call it first vowel. So if first vowel equals -1, then just return true.
This one right here.
Okay. Well, we'll just have to make do with that, it looks like.
It is streaming. It should be good.
Okay.
So I don't see it. So I might have accidentally set it as unlisted.
All right. Well, I need to get started.
Just get that.
Okay, let's get started again.
First vowel string is going to be in parentheses. Equals 1, then we count something else if it equals 0, which means it's the first character. Else, everything else is going to do. Yeah.
Okay, so here we are. We want to write some accumulation loops. And again, the bones of it are the same as for all the other loops. So we start with an enumeration loop, and then we elaborate a bit. So for integers, it's going to look, in this case, like we're going to start somewhere. Int I equals 1, yi is less than or equal to n. We do something, then we're going to have to increment I. I will show you this one here. So what that does, that I plus equals 1 is the same as I equals I plus 1. And you can do that for other operations. You can say I minus equals 1 or I times equals 1. So it's just a shorthand for adding 1 to I. Okay, so there's the basics of an enumeration loop for integers. And we've got to find the largest integer. So to make an optimization loop, first of all, just like an accumulation loop has an accumulation variable, you've got to have a variable to hold the largest thing seen so far. Okay? So I'm going to declare it. What type should it be? Okay, so the return type of the method will tell you what the type ought to be. So we've got to have something, I'm going to call it largest so far. Now, the question then becomes, what should you initialize it with? Yeah? Integer dot what? He suggested integer dot min value, which is the most negative integer. I've got a different idea. Notice that we can assume that there's at least one number in the interval. N is at least 1. So the loop's going to go, there's at least one number to consider. So in the case where you know the interval is not empty, what's a logical thing to prime the largest so far with? Yeah? Just take the first element in the sequence, make it 1. So we'll set that to 1, because that's the first number we're going to consider. And then there's no need to start with 1. What should we start I with? 2, because we've already considered 1. So we take the first element and make that the largest so far. And then we just, our loop just runs one fewer time. We don't consider 1 in the loop. We start with 2. Okay? What do you suppose has to happen after the loop ends? We need to return the largest so far. So that's sort of reminiscent of an accumulation loop. And then, just like an accumulation loop updates the accumulation variable, we've got to possibly change largest so far. So how do we update largest so far? Yeah?
If n is greater than largest so far equals.
The loop is the right idea. This is what we want to do. Basically, if I is largest so far, what should we do? If it turns out that the iteration variable I is the largest so far. Right. We do largest so far gets I. Now, under what circumstances should I become the new largest so far? Yeah.
What has to call the static method, like match all cosine.
All right. So if the cosine of I
Greater than match cosine I plus 1.
no. If it's bigger than the cosine of largest so far, we have a new champion. So largest so far is not the largest number so far. It's the number with the largest cosine so far. So maybe I should call it number with largest cosine so far. All right, I would probably never do that in a program because it would take too long to type, but maybe so this is clear. When you look at it later, we'll do that. It drives home the point. Okay? So that's a prototypical optimization loop. Assuming the interval is non-empty, you can prime the pump. You can start the I generically call that variable best so far. So we would, the initial best so far would be the first element in the sequence. Then we look at the rest of the elements of the sequence, and each time we find one that's better, that becomes the new largest so far, the new best so far. And then when we're all done, we return what we found. All right? Any questions about that? Yeah? That is, it means exactly the same thing. It's just a shorthand. So if you ever have an operation that's I equals I and then some operator and then something there, you can just say plus equal. Yes?
Since number with largest cosine so far is a ridiculously large name, would we be dog
I have to admit that a number that long is kind of annoying. I would, you would not be dog points for it, but it would be. It doesn't, despite how descriptive it is too long. It's kind of annoyingly long. But I didn't want there to be any ambiguity here. All right, let's find the largest character in a string. So what will the enumeration part of this, again, is going to be int I equals 0, while I is less than s.length. This is just a standard way you go through a string. We'll do something, and then we got to add one to I. Okay, so that's the bones. How do we turn this into an optimization loop? Yeah?
First, we need a variable that holds the largest character so far.
Okay, so we'll declare a variable of what type? All right, it's supposed to return a character. So our best so far, char, we'll call it largest so far. And how do we initialize it? Someone else tell me how to initialize this thing. Yeah? Right, we take the first character off 0. because we're guaranteed that S is not empty. Now, having done that, having chosen to make the first element the value of largest so far, what do we change about the bones here? Yeah. Right. We start the index at 1 because we already dealt with 0. All right. Now, when we're all done with the loop, we're going to return largest so far. And inside the loop, we put a conditional to maybe update largest so far. And again, there'll be some condition. And if it's true, we will say largest so far equals what? Is it equals I? Right. We want the character at index I. Okay. So all that's left is that conditional right there. Take a minute and see if you can figure out what's the condition. Under what condition do we replace largest so far with a new character? In particular, I don't want an answer right now. I'll take questions. I want you all to think about it. Talk to the people around you. Think about it. Don't just wait for me to show you. You don't want, when you work on the assignment, be the first time you've ever thought about something like this. And you people listening at home, think about it too. Don't be passive participants. Okay, who could tell me what to put? I want someone new to tell me what to put. Okay, what do I put? Right, so if the new character is greater than the old one, then we found a new champion. Then we're all done. We'll have the best overall that we'll return. Hey, any questions I could answer about that? Okay. What about find longest token? So we're given a scanner, and we're supposed to return the longest token that it contains, and we're allowed to assume that the scanner is non-empty. Say what? Well, it's a similar thing. What do we start with? Yeah?
Longest token equals S dot.
Well, getting a little bit ahead of ourselves. Before we even get to worrying about what kind of loop it is, what do? Yeah? Well, the scanner is passed in, so you can see the scanner is a parameter right here. Yeah, well, you would go find the most, the most similar optimization loop and plug it in. I don't happen to have one handy, yeah? Well, what I want someone to say is we'll do something like this. While S dot has next. We write the stuff that's common that you use no matter what kind of loop you're writing. And we're going to have to pull a string out. Okay, so that's an enumeration loop for scanners. Now we have got to turn it to an optimization loop. And that's what everyone else was trying to answer. So, turn to an optimization loop. What do we need first? Go ahead.
You create a string with the longest definition.
All right, so we'll call it longest so far. worry about initializing it in a second. When we're all done, we're going to return that. And following along on the theme that we've seen so far, the scanner is non-empty. So what should we initialize longest so far to? Yeah? Right. We just take the first thing off of, so we just take the first token off the scanner. Now, do we need to change anything about the enumeration loop like we were doing before? In the other cases, we had to start I at 1 instead of 0. Make sure I did the right thing here. Yeah. Sorry about that. Do we need to change anything? Got an answer? Anyone want to go out on a limb? Yes or no? Do we have to do anything to account for the fact that we just read something off the scanner? Yeah? Right. He said no, and that's right. You know, we read thing off the scanner, now it's gone. And so when the loop first calls s.next, it'll be getting the next thing on the scanner. So the act of calling s.next is all the change we need. The scanner's been modified. Okay, so we get the next thing off the scanner. What do we do? Okay. Go ahead. Mm-hmm.
And the condition would be if the length of the token is greater than the length of longest so far.
So if the length of the token is greater than longest so far dot length. So if the new string is longer than the old string, typed in the wrong place. We update longest so far. Okay. So there's an optimization loop written to consume a scanner. Now, what if the length method were really expensive? Length is a very efficient operation, but what if it were really costly? What if it cost you $10 every time you called it? How could you make this method half as expensive? Yeah. Okay. Compare to is expensive. How could we not call? Yeah.
We can create a variable for longest so far dot length.
Right. So notice every time through the loop, token is new. You've got to find its length. But you could end up computing this over and over again. So one thing you could do is, in addition to having longest so far, you could also have a separate variable that stored the length of the longest so far and update them both in here. So when you find a new longest token, let me just show you how that would work. So we would have int, we'll call it longest length. And what should it be initialized to? The length of our initial longest so far. Now our goal is to only call length once for each token. So what's the first thing we got to do when we get in this loop? Well, let's not worry about that. What could I change about this conditional so we don't have to call length twice? Think about it for a second. What you got?
So instead of calling longest so far dot length, we just call longest.
We don't have to call it, we just use it. Longest length contains the length of longest so far. So we don't have to recalculate the length, we'll just use that. Yeah?
Again, we have the longest length is equal to longest so far dot length.
Right, we changed longest so far, we better change longest length. And that will be longest so far dot length. Okay, so we're no longer having to calculate over and over again the length of longest so far. Okay? Now, would it be the same thing here? Instead of longest so far dot length, would it work to say token dot length? Would that amount to the same thing? Yeah, because of that assignment up there, longest so far and token, at the point that we get right here, they refer to the same string. So we could do token dot length. But now look, we're computing token dot length there. We already computed it here. We're wasting $10. What can we do? Yeah.
Well, I was just going to say, if you had updated longest length first, you would have had to do token.
Well, he's saying if we'd updated longest length first, well, then we wouldn't have to do this. We still got to calculate. We've got to give a new value to this. How can we avoid the price of doing that when we already did it up here? Okay, make a new variable. Let's just make one called token length. As soon as we get a new token, we'll calculate its length and save it. Okay? So we've calculated the token's length, and then instead of calculating it there, we'll just reuse our previous calculated value in two places. Great. So now, if there's 10 tokens, we're going to calculate the length of tokens 10 times. That's the minimum number we can get by with. Every token gets its length is calculated once. So what do you think about that? Does this make the program easier to read and understand? I don't think so. I think it makes it more complicated. But on a million element string, on a million element scanner, it would save $10 million. So probably a good trade-off if that were the actual trade-off. You often see this. You can come up with a simple way of doing something, but it turns out it's just too expensive, not in terms of dollars, but in terms of time or memory or something like that. And so you have to work a little harder and make the code a little more obscure in order to make it faster. In this case, if you make it more obscure, then it starts to make sense to start putting comments in here to explain what's going on. Explain the relationship between longest so far and longest length. Maybe say why you're doing something, so the person that reads it after you's got a chance to figure out why you did this. Now that's more of a topic you talk about in 2420, making programs faster. We're just sort of worried about making them at all right now. But I wanted to point this out. Okay, so before we go on, look at another example. Any questions I could answer? Yeah.
When it wants you to put, when it wants multiple outputs after a return, so it says find the biggest one and post it, and find the next biggest one and post it. You should write on that.
Okay, you said something in the beginning about this had something to do with the assignment or nothing to do? Okay. All right, so he's asking, essentially what he asked, suppose you've got a collection of things, you got to deal with them in sorted order, like in ascending order of length or descending order of length. And that problem, that's a well-known problem. It's called the sorting problem. And that's something you study to death in 2420. But next week, we'll start looking at collections of things. And there are methods in the Java library that sort lists of things into whatever order you wish. And we'll look at that at that time. Any other questions? Yeah?
I understand the longest length, like keeping it as a semi-permanent integer, but token length, if you put it right there, isn't it calculating it each time? I mean, is there...
No. This method is called once. And what is stored in this variable is the answer. So when you use it here, you're just looking up the previously stored value for longest length. You're not recalculating it. Thank you.
I'm saying, is it necessarily efficient to make that particular thing?
It depends on how smart the compiler is. Now, probably the Java compiler, since it knows that the length of a string can't change, it probably would automatically calculate it and save it. So this one is probably superfluous. But, you know, this is sort of an extreme. In fact, the way strings are written in Java, if you calculate its length once, the string I think the string just saves its length internally, so it can answer that question faster the next time. But sometimes you get a situation where if you don't do this, you end up paying a real cost. You can have really expensive operations. I'm definitely overstating the case right here. Any other questions? All right, so now we got to find the integer with the most factors. And this time, n might not be positive, in which case what that means is there's no interval to iterate over. So now we don't have that, we can't assume that there's at least one integer. So we're supposed to return 0 as our answer. So that's going to be a little bit different. Let's go up here to get started. Largest cosine, and let's copy this. Because that's the right kind of optimization loop. It works over integer intervals. And I'll come down here and paste it in and we'll fix it up. So what would be a better name here? You got a suggestion?
Number with most factors so far.
Number with most factors so far? Yeah, but I'm not going there again. That's just too long. Yeah? Okay. I'm going to call it so far. Just to remind you, if I can't think of anything better, I use best so far as my variable. Okay, now our condition is going to be completely different. I'll clear this out. And this is going to be, that's going to get updated at some point. We're going to return this. Okay, but now we've got a problem, which is, how do we initialize most factors so far? How do we deal with the fact that we can't initialize it to 1, because 1 may not be a member of the sequence. N might be 0. So if n is 0, there are no numbers to work with, and we want to return 0. So what strategies can you think of? Yeah? Well, no, scanner wouldn't help here. I can think of a couple of ways to approach this, yeah?
Just a feeling this isn't what you're looking for, but could you just say if n is less than 1, return?
You could definitely do that. So just before you do anything else, you could just test it. You could say if n is less than 1, return 0. You could just test for it. And then you could write the rest of your code safe in the knowledge that there's going to be at least one number, and write it like before. Okay? So just having noted that's a possibility, let's see if we can do without the if. Think about it this way. Suppose n is 0. How many times will this loop run? No time, it won't run at all. So whatever the initial value of most factors so far is, that's what will be returned if n is 0.